Good afternoon, centers, coordinators, and participants. We will spend about half an hour in going through some of the simulation exercises, and the idea is basically use of simulation in teaching a course on basic electronics. Right now, some of the centers have already informed me that they would be using not the SQL simulator, which we had recommended, but they are more familiar with some other simulators like PSpice and TINA or whatever it is, and so they are free to use these other simulators, but do the exercises that we are recommending, so that the participants benefit from the content. So the objective really is not so much to learn a new simulation package, but to use simulation for teaching basic electronics. So that we should keep in mind. That is really the first and foremost purpose. Alright, so those who are using SQL, if you have been to the SQL website, there is a set of simulation exercises here. All the coordinators are requested to maximize their screen so that they can view things properly. It's not so important to view my photograph at the centers. You will see that tomorrow again. Alright, so there is a link called simulation exercises, and just click on that. You will have a number of exercises listed over there. Now we will only go through some of these, and again the important thing is to for the participants to try out some of these and think of how these are useful in teaching really more than it's not the mechanical use of a simulator, right? It is really using a simulator to teach. So let's look at some simple examples. Let's start with okay, so let's look at an RC circuit, a simple RC circuit with periodic input, and the document for that looks like this. Alright, so in this problem this RC circuit is being driven by a square wave, and as you change R and C, this waveform is going to go up and down, and there is an exercise which says that you show certain things. Now these are things that you can actually work out at home and not in this session, but it's very important that you do this and you get your students to do it as well, because it brings about a lot of fundamentals very clearly. Okay, so in this exercise set, what we have said is for R equal to 1K, C equal to 1 micro, and T equal to 2 milliseconds, simulate the circuit for different values of T1 and T2. Right? What is T1 and T2? T1 and T2 are these high and low periods. And if you do that, you will observe that this waveform will shift its DC value, and that is only natural because it follows this particular relation, and you must show that on paper. Alright, so that is one. So that's for different values of T1 and T2, and in each case compare the simulation result with the expressions given above in the document. Right? That's one. Derive an expression for the current in steady state. For the conditions in 1, validate your analytic result with simulation. Alright, so let us, this example is already there. All of these examples are in fact there in the SQL distribution as it is, and you can run that, or you can use, some of you have said that you will use some other simulators like Proteus and PSpice, and that's also fine, but make sure you do it. Right? So let's look at this example in SQL. The name of the file is given this at the top of this document, right? So the top of this document says E101 underscore RC1B, and that is just a standard extension for SQL project. So if you look, when you try to open a file, you look for this particular name, E101 RC1B. Okay, so there it is. Open it. Alright, so that is what it looks like, and this says that the R value is 1K, C value is 1 microfarad, so it's already ready made for you, and high voltage is 1, and T1 is 1 millisecond, T2 is 1 millisecond. To run this program, or run this particular example, just say run solver. Alright, you will see a message here called program completed, and once you see that, the control will automatically go to graphs, right? And the graphs, you will see some files which we have asked for, and you can choose an x-axis, and so most of the coordinators will be familiar with this, and they will be able to explain to you better. Alright, choose the time as x-axis, and for example you can choose the input voltage VA and the output voltage VB as a y-axis, and then just say graph it. Okay, when you say graph it, you will be able to see a plot. Now in this particular example, we are interested in the steady state part, not in the beginning transient. And note in particular what this value is, what is the average value of the output voltage. So I'll just do this for you, and then you can do the others yourself. So in for example here in this exercise we are saying try this out for different values of T1 and T2, and we have just tried T1 equal to 1 millisecond, T2 equal to 1 millisecond. Now let's try this, for example, T1 equal to 0.2 millisecond, T2 equal to 1.8 milliseconds. So let me go back to the circuit editor. Let me click on this element, because those are the properties of that element. Go to this property editor, and then there is this T1 here, which is 1 millisecond right now. I can change that to 0.2 millisecond, and T2 I can make 1.8 millisecond. And with that I can run this the program again and view the output results. Okay, and that is what we see. So you see that the average value of the VC waveform has shifted up, and all that of course is because because of good reasons, and that is this. All right, so that's just an example of what you're going to do in this particular RC circuit example. Let's go to some others. Okay, let's look at an RLC series circuit, resonance series RLC circuit, number 4. If you click on that, it says, it just gives you a brief description first. What is the current in a series RLC circuit and so on. And the following results hold for this circuit in the sinusoidal steady state. The total impedance seen by is minimum and so on. Of course, all of these are standard results. What is not standard is the plots that you can view with a simulator, and that very often we have not seen all of those plots, and it's very important that we do that. So let's look at the exercise set. So first, for some given values of R and L and C, calculate F0 and the bandwidth. Verify with simulation. So how would one do this? Let's look at the name of this file here. It's called E101 Reso RLC1. Okay, so let me open this file. It's in E101. Okay. All right. So that's a series resonance, series RLC circuit, and there are some meters here which measure some voltages. Right now, let's just ignore it. So let me run this solver, run this circuit, and look at the magnitude of the current versus frequency. So I chose frequency on the x-axis and magnitude of the current on the y-axis, and let me say graph it. Okay. So that is what I see. And remember, in all of these circuits, the frequency should always be on log scale. Otherwise, you can't really resolve things properly. So let's choose the x-axis to be a log axis, and now you can clearly see the peak. So the peak is between something like 5000 hertz or 5 kilohertz, and that is what you should get as the calculated value as well. All right. Are there any questions at this point? Silence. No, are there any questions at this point? Is there any way to invite questions? Or okay, let me just take 2 questions, because otherwise we'll spend all the time in question and answer right now. Okay, so let's so the question from Professor Marathe in KJ Somaya College is whether we can go through a trial session using sequel from start to end. That is, start an example and see how it is to be constructed. All right, so let's do that. Fine, okay. So let me take, for example, this first circuit that we saw, right? This RC circuit with a periodic input, and let's construct this from scratch. Although we already have it, let's just go through that exercise so everybody knows what is to be done. Okay. All right, so let's open a new project, and since in this case I already know which components there are, we are going to use a clock, we are going to use an R, and we are going to use a C. Okay, so let me get all those components first. That can be done. The easiest way to do that is if you know the name of the component, type that name of the component. And so in this case R.ECE. Now ECE, as we said earlier in the workshop, it stands for electrical compound elements, and that string will show you everything, all the components that end in that particular sequence. Okay, so there is a R.ECE, a resistor here. So I select this resistor with a single click, and then I take the cursor to the canvas, and then I double click here. So then this component comes to the canvas, and so on. I can select a capacitor there, and then I can select a clock. Okay, a clock is a voltage source. All right. Now this capacitor is not looking right. I would like to change its orientation. So I can do that. There are different ways of doing it. The easiest way is to select it with a single left click, and then press R for rotate, and that will get rotated. And of course, if you want to move things around, you can select them and move it like that, or you can select and use the arrows, etc. Right? Okay. Now, so let's make the connections. Apart from this, we also need a ground. So let me look for ground. There is ground, and let me place it so that I can make connections easily. All right. The next step is to complete the wiring. So click anywhere on click on one of the nodes. All right, and then you will see a crosshair. And if you want to introduce a bend, okay, just do a left click there, and then click on the node where you want to end it, and then the wire will show up. Okay. If you make a mistake like this, suppose you want to get rid of this file, you can just press escape and it will go away. You can zoom in and out by using the mouse center key, or you can also use these zoom out, zoom in options in the menu, in the top menu bar. All right, so let me complete the wiring. All right, that is done. This resistor, I would like it to be 1K. So I click on this property editor, and then you can see there is a property called R. Now that property I want it to be 1.0K. I can write this as 1.0K, or I can write it as 1.0E3, or I can write it as 1E3, and so on. Any of these things are okay. So it's 1K. This capacitance, I would like it to be 1 microfarad, so it's 1 U for micro. All right, then this clock, I would like T1 to be 1 millisecond, T2 also to be 1 millisecond. Can you reduce the AC a little bit? It's a bit too cool. V high equal to 1, DT1 0.01 millisecond, DT2 0.01 millisecond, and so on. Okay, some of these things you may not know what to put. In that case, you just do a right click on the element and say element help. Okay, and then you will see what is what. For example, here is a document on clock.ece. Okay, it tells you what are all the various parameters. All right. So now I don't suppose you want to see the value of this resistance on your canvas. There is a way to do that. So you do a right click and say add element property text box. Select this element and select the property that you want to display. Okay, and then you get this. You can of course move around that box and so on, etc. So you can do this pretty much with all the components. That way you have a visual feedback about the values. All right. Let's move on to output variables. We would like to define some of these variables for viewing as output variables. So go to output variable tab, click on add variable, and then click on one of the wires that you want to see, the node voltage. Okay. All right. So that has come. If you see, there is a default name that is generated, and then there is something called a keyword node V of something something. Right. So that something something is the name of this node. This node name can be changed. For example, I can select this. I can go to property editor. I can make this A, for example. All right. So then in that case, this will automatically change in the property editor. I can also change the name of this variable, and in this particular case, it makes sense to call it V A, for example. All right. Let me add another output variable, and that is the node at the voltage at this, or the node voltage at this particular node, and let me call that V B, and let me also name this node as B, and I'll name this node as 0 because it's ground, although that's not required. Fine. So the output variables are two in our case, VA, node V of A, and VB, node V of B. If you want to display the name of this node, just go to element property text box, select this resistance and select N node, for example. That is where that B is connected, and say OK. Then the B will come here, and then you can move that around if you want. All right. What next? Next step is to tell the simulator as to what we want to do with this circuit. Okay, and so you go to solve blocks, add a solve block. The default type of the solve block is DC simulation. Click on that, and you can change that to transient. In this case, we are interested in transient or time domain simulation, so change that to transient simulation. When you click on transient simulation, some of these things will come up by default. So the starting time, the ending time, and the time step. So ending time, in this case I would like it to be, let's say 10 milliseconds, delta t maybe 0.01 millisecond. All these things, of course, you need to know how to choose, and that will take some effort. So the best thing is to go through some existing examples, see how it is done, and then do your own examples. All right, the next step is we need to choose a method for solving the equations, and a good method, a very commonly used method, is the backward Euler method. So in this, on the left hand side, you will see backward Euler. Just drag it and drop it in this box, and then you can change its properties. So here by the default is no, so if we want to make it a yes, okay, so then that you can do on the right. One more thing that we need to do is to put an output block. So take an output block, and we need to add output variables. So click on output variables, select VA, VB, and say OK. So all that comes on the screen. Okay. I think that is more or less all. Now we can run the program, and once the program runs successfully, you can see this message here: SQL program completed. And then you get to the graphs menu. So select the output file. Sometimes there can be more than one file if you have defined more than one. Select time as the x-axis, and the input voltage and the output voltage on the y-axis, and that is what you get. All right. So this is how you go through the basic sequence of making a simulation, designing your circuit as well as running the simulator. Let's invite some questions. Okay, the site is and you can if you are using Windows, you can download the Windows version. and there are instructions then to install it. Your coordinator would have probably already done that in the lab. I just ask the coordinator first.
Sir, we are not to get video audio signal up till now. So, would you please explain some important points again about SQL software?
All right. So there was a question from KK Wag College, Nashik, and they were not getting the video, and they want me to explain some of the basic points once again. All right. So let me just quickly do this. So if you want to create a new circuit, click on New here, and you can get the components that you want from this menu on the left hand side. You can search. You can click on the left window, and then you can double click in the canvas, and the component comes there. Okay, so I wanted R, C, and clock, and then I also want the ground. So there is a ground element here. Okay. To rotate an element, just select it and press R. That rotates. To edit the properties, click and select property editor, and then you can edit the property that you want. So here, for example, for R, I will take 1.0 K. C, I will take as 1 U, which is 1 microfarad. And for clock, I will take T1 as 1 millisecond, T2 as 1 millisecond. DT1, DT2 are the rising and falling edges. I will take that as 0.01 millisecond each. It should be smaller than T1, much smaller than T1 and T2. After that, the wiring. So click on a node, and if you want a bend in the wire, click again and then terminate it, and so on. All right. After that, if you want, you can name the nodes. You can name the nodes either as properties of an element, or you can edit it directly. All right, then define output variables, add variables, say this voltage and this voltage. You can change these names. Then you need to go to solve blocks, add a solve block, change it to transient simulation. Select starting time, ending time, and the time step. Okay, then you need to select a method. There is a method called backward Euler that is very convenient and most commonly used. You can make that yes by because the default value is no. Then you can put an output block, and you can select output variables VA, VB. That's it. Now you are done with the solve block as well as the circuit. Now you can just run the solver and view the results. All right. So now if you are using SQL, this is the procedure. If you are using some other software like Proteus or Tina or whatever, then the coordinator at your center will explain to you what to do. Now in the rest of the time, what we will do is we will just look at some exercises. We will not really build them, but we will just look at the existing SQL files, and I will try to emphasize on what you should observe and what you should have your students observe when you teach in courses. So I was looking at RLC. We have finished that. I don't have too much time, so let me just look at some 4 or 5 more examples, and then we will let you work on these yourself. All right, so there is an example for diode clipper in E101. It's called E101 diode clipper 1. Okay, so here is a very simple clipper. It is driven by a triangle source. R equal to 1K, and there is a DC voltage source of 1 volt in series with the diode. Alright, so we run this and we can observe, we can select x axis V in as the x axis, V out as the y axis, and we can have a graph of it. Right? And that is what the clipper will do. Okay, and of course it's important that you ask your students to figure out what this value should be, what this should be, and so on. Alright, now this is fine, but you would also like to see what the current is in the diode. So if you look at the circuit, this diode will start conducting only if this voltage exceeds about 1.7 volts, right? And so that is important to show the students. So let me go back to the graphs menu, select the current as well, and let me select the right axis for the current, because it will have different, very different number. It will be in milli, that means 10 raised to minus 3, whereas the output voltage is in volts. So therefore I would like that to be on the right hand side, and then graph it. Now I can see these two together. So you can see that the green line is the diode output diode current. So the diode starts conducting at about 1.5, 1.6 volts, and then it and this slope of course will then be given by the resistance in the circuit, and that is the output voltage. So it's very important to view these two together so that the students get to know exactly how the circuit works. You can also look at things in the time domain. So that is the time domain. So this is the output voltage. Let's also see the input voltage. Okay, so that is the time domain. So the input voltage is green, the output voltage is pink. Sorry, the output voltage is blue, and then the diode current is in pink. All right, so that is, and you can of course make these things more complicated, introduce one more diode and so on, and ask the students to play with it. So in the process they learn about diode circuits. All right, there's a rectifier example, E101 rectifier tab 2, or sorry. I think it's in diode circuit rectifier tab 2. Yeah. Okay, so here is a rectifier with Zener diode regulator, and it's ready made again. So you can just run this circuit, and then there are exercises. Like I said earlier, you can go back here. You can see rectifier. Okay, so there is the basic operation of the circuit is described in this document. The name of the file appears on top, and then the student is asked to do a few things so that the understanding improves. So for Vm equal to so and so, Rs and R and so on, work out the following quantities analytically: average value of the capacitor voltage, ripple voltage, average current through D1, D2, peak current through D1, D2. These are not easy, but it's a very definitely a worthwhile exercise. Maximum reverse voltage appearing across each diode and so on, and then you can do the simulation and verify that your understanding is indeed correct or not. So the diode currents, for example, all right, clearly one diode conducts, then the next, then the first one, then the second, and so on. Capacitor voltage, source voltage. Okay, so that is the source voltage, and that is the capacitor voltage. You can expand this capacitor voltage to see the ripple, and you can see this ripple. If you want to expand it further, that's what the ripple looks like. And you can actually measure. You can from this graph you can see what that ripple voltage is and verify that with your calculations. Okay, you can also look at the voltage at the load, that is the output voltage, and that is of course regulated. Therefore, it's much better than the capacitor voltage. So that's at 5 volts because it's a 5 volt Zener, and you see the ripple is basically disappeared. Okay. Okay. All right. So that's the rectifier example. We'll just look at 2 more examples and then maybe 3 more examples, and then we will let you work out things yourself. There is a question. Okay, how to so there's a question which says how to choose a method to solve blocks in the solve blocks tab for a particular circuit, and is it different for different circuits? Of course, it's different for different circuits. It depends on what you want to do with the circuit, whether you want a DC analysis or a transient analysis or AC analysis, for how long you want to observe the output, for what range of frequencies and so on. So all of these things will depend on the circuit. And there is a detailed manual. If you go, how do I get back to that one? Okay. If you just go to the top, to the tab at the top, there is a manual here. Okay, this manual explains all of these things in more detail. So as I said earlier, this is not something that you will pick up in one day, but you can get started today and go through this manual in more detail, and also use the existing examples, see how things have been done, and then that will certainly give you more confidence in using the simulator. All right. So for today, I would say play with these existing circuits, change component values, see the results, and the important thing is not to use the simulator as a toy that anybody can do, but learn something from the results. Okay, let me look at a BJT mirror one. BJT circuits. So there is a mirror circuit, very simple mirror circuit. Okay, and what do you look for in a mirror? You look for mirror in the output resistance, output load, or the load, which is constant more or less irrespective of the voltage, the output voltage. Right? And let us see how this circuit performs. So let's run this circuit, and I would like to see the input voltage as the x-axis, output voltage as the y-axis, and let me graph this. What happened? Sorry, just the opposite. Okay, let me choose. Made a mistake. Let me choose the output voltage as the x-axis, and the collector, the IC1 and IC2 as the y-axis. Okay. So here is, so this part, the first part, the transistor is in saturation, and we don't operate in that region, so we can actually ignore that part. So we should actually focus on this particular part, and you can see that the output current is not quite constant. Okay, so this is the input current, and the output current actually varies with the output voltage. So that is not very desirable. Although the variation is small, it is not very desirable, and that's why there is an improved BJT mirror which is used, and that circuit is BJT mirror 2 in this particular set. So look for BJT mirror 2, and that's a cascode mirror. Right? Here once again the objective is design a certain output current, and we want it to be independent of this voltage here. Okay, so let's run this solver and see how this performs. So let me take VC4 as the output voltage, as the x-axis, and the load through the resistor as the y-axis. Or that is the same as this IC4. Okay, so that's what I'll do. VC4 as the x-axis, IC4 as the y-axis, and graph it. Okay, now you can see that the variation with respect to the output voltage is very, very small. Okay, you can actually see how much it is, and you can see a huge improvement over the previous circuit. And of course, you need to figure out why that is happening, and that is happening because of this cascode connection. And of course, the rest we will leave to you. All right, so let me take one more example with an op-amp, for example. Okay, op-amp triangular wave generator, for example. Okay, so this is based on the op-amp used as an integrator and another op-amp as a Schmidt trigger. And so that is the name of the circuit, op-amp, the name of the file. Let's run this and see what happens. Op-amp OSC1. there it is. Right. Okay, so this is already wired for you. You just need to run it. And that is what you get at the output. And of course, the important thing is not to just look at the output, but what is happening also at these other nodes. Right. So that is, for example, what is happening at node 6, what is happening at node 5, that is just a constant. What is happening at node 4, what is happening at node 3, and so on. Let's look at node 3, node 6, and the output. Okay, and of course you will see this triangle at as the output of the integrator, and so on. So figure out how this works, and then there are of course some exercises. So repeat 1. So do all these things, then repeat 1 for Vs equal to 2 volts. There is a voltage source here, a DC voltage source, right? So you need to figure out what happens if there is if this is 0 or 2 volts or minus 2 volts. How that will change things. It's very interesting, and if you actually figure that out on paper, your understanding of this circuit is perfect. And so the same goes with your students. What is the purpose of this resistor R limit? Okay, this resistor here. All these questions are very important, and that is how I mean you should use a simulator to also answer some of these questions. Okay, so I will stop at this point, and I will let you have some fun with at your end, but we can take a few questions. Okay, so there is a question which says give a demonstration of a digital circuit. Okay, so just take one example. Go to, there is a directory called digital circuits. So let me take up down counter, for example. Okay, so here is an up down counter. Okay, it's essentially there is a mode input, and then there are these flip flops. And if the mode is 0, then it counts up, and the mode is 1, it counts down, and so on. It's a standard circuit, binary counter, and all J's and K's are equal to 1. All of these J's and K's are tied to 1. All right. So this digital circuits will run very fast, and you can view the clock, the Q0, Q1, Q2, Q3, etc., all at the same time. Okay. So you can clearly see the counting operation. If you change the mode signal, it will count. This is counting up. Right. Then it will count. If you change the mode signal, it will count down. Okay, so we can verify that. Any other questions are there? How can we plot current? How do we select the variable type? Okay. All right. So let me take an example. All right, so there is some existing example, and I want to see the current through this particular resistor, for example. All right, so what I do is add variable, go to the output variable tab, add variable, and click on this R, and then I can select I1, which is the current through that resistor, as the output variable. Okay, and then you see here I1 of R because this name has got this resistor has got name R. I can change this if I like. I can make this I R. All right, so that should answer that question. Anything else? One demo for sinusoidal source. Sinusoidal source. Okay, let me take a power electronic circuit. Here is a sinusoidal source. Is that what you mean? Okay, so this is a circuit in time domain. All right, and this if you look at the properties of this sinusoidal source, it has got the amplitude A, frequency in hertz, phi and T0 and VDC, and of course you can look at the documentation of this, and it will explain what is what. Alright, there is another, if you want to look at a sinusoidal source in the complex, in the frequency domain, there is already an example for the resonance. E101 resonance RLC 1, this one for example. Here is the same AC source, same element, but now the solve block is AC simulation. Right? So that means we are in the frequency domain and not in the time domain. So when I run this program, this circuit, I will get frequency as one of the x-axis values, and then I can plot the magnitude. That's it. In the rectifier experiment for a sinusoidal input, the output obtained was almost 0. Please explain. Okay, let's get back to that example. Okay, this is the example. Let me run it. So there is the input here and output are here. So the input is large. The output, there are two outputs. One output is the output at the capacitor that has got a ripple, and the other output is the output at the Zener, and that has got no, very small ripple as expected. Alright, so the question is, why is this output voltage small? And that is simply because of the transformer. It's a step down transformer, and that is stepping down the input voltage. That's why the output voltage is very small. That will simply depend on, if you are curious, you can always change the turns ratio of this transformer and you can make it larger. I think that's it. Okay, so I'll take your leave, and I'll meet you tomorrow again.